Hi all. Today I'm going to be covering the concepts in Chapter 6, Section 2, the truth functionality of the operators that we've covered. By the end of today's lesson, I'm trying to get us to the point where we can solve the following equation given truth values for statement variables z, x, a, b, and c. So if we were given that x and z are false, and if we were given that a, b, and c are true, we need to be able to figure out if this longer proposition containing all these statement variables is true or false. So that's where we're trying to get. Let's see if we can get there. The first thing we need to talk about is, what do I mean by truth functionality? So all of these operators, the tilde, the wedge, the dot, the triple bar, and not in this problem, but the horseshoe, are truth functional operators, meaning they bring together statement variables they have an effect on the truth value of statement variables, an effect on the truth value of the entire proposition. So we have statement variables, we have truth functional operators, we put those all together and we get an output of either true or false. So what we need to talk about is how the operators affect the truth value of statements. So think about, by analogy, think about what the way operators work in math. So we might have something like 3 plus 2 times 2. So what do those operators do to give us a number? Well, the multiplication symbol will tell us that we need to multiply these two numbers together, and then the addition symbol tells us we need to add the 3 on. We have an order of operations. We know what the operators do to the numbers around them, and that's what allows us to get an answer. So first, our order of operations would tell us we do 2 times 2. First, to get 4, we add the 3, so we end up with 7. Once we know what the operators do with the things around them, and once we know the order of operations, we can solve. Our task is a little bit easier because in the math that we'll be doing, there are only 2 values. There's only true and false. So we don't have to deal with all these different kinds of numbers. There are 2 values for statement variables, that's true or false. So each of these is either true or false. And then the operators will tell us about they'll have us perform different operations that will have an effect on the truth or falsity of the proposition as a whole. So there's what we're doing by way of introduction. Now we're going to focus a little bit more, well, quite a bit, on each operator, the truth functionality of each operator. So the first one we want to talk about is negation. So represented as a tilde in our text. On the keyboard, since a tilde is not immediately accessible, I'm having us do the hyphen, so tilde p. So take a statement that's true. A statement that's true is the Warriors won the 2018 NBA championship. Let's say that is our statement P. And here P can stand for any statement as simple or complex as you can imagine. So in this case, I'm having it be a simple statement for ease of example, but you could have it be a very complex example. So P in this case is the Warriors won the NBA championship in 2018. Now that statement is true. So what if somebody said it's not the case that the Warriors won the NBA championship in 2018? Well, they would have said something false. So the Warriors won the championship. In this example, that would be our P. It's not the case that the Warriors won the championship. That would be our tilde P, or our hyphen P. So when we say, if our simple statement is true, and we put a tilde in front of it, well, now the entire proposition is false. What if the proposition is false? What does putting a tilde in front of it do? So take a simple statement like the Cavaliers won the NBA championship in 2018. That statement is false. So what if we put a tilde in front of it and say it's not the case that the Cavaliers won the championship in 2018? Well, now we would have said something true. So what does the tilde do? The tilde just flips the truth value. If our original statement or proposition, regardless of how complex, was true, then it flips it to false. If the original statement or proposition was false, then it will flip it to true. All right, so that was our one place operator, negation. The tilde just negates whatever comes after it. Then the rest of our operators are two place operators. So where negation just works on whatever comes after it, so we can represent that just with P. And P has two possibilities. It's either true or false. Our other operators are two place operators, so we'll need to have a larger table to talk about their truth functionality. So the next one that we will want to talk about is conjunction. So conjunction, the dot is what we use to symbolize and statements, moreover, but, etc. We would symbolize all those kind of statements with dot. So the dot brings together two statements or propositions, so P and Q. Here the P just stands for everything that comes before the dot, and the Q stands for everything that comes after the dot. So what happens when both sides of a dot are true? Well, let's think about an English language example. Imagine you order cake. You're at a restaurant and you order cake and dessert, cake and pie. Let's do it this way: pie and cake for dessert. And the waiter repeats your order back to you, and he says, you are going to get pie and cake for dessert. Under what conditions would his statement be true? Well, let's say he brings you both pie and cake. Then clearly his statement was true. He told you you'd get both pie and cake. He brings you both pie and cake. That's a true statement. Let's say he brings you pie, but he doesn't bring you cake. Well, then his statement is not true. He said he'd bring you both. He only brought you one. Let's say he does not bring you pie, so it's false that he brings you pie. It's true that he brings you cake. Well, then again, his statement was false. He said he would bring you both. He failed to bring you pie. And let's say he tells you he's bringing you pie and cake for dessert, and you get neither. Well, then you're really upset. He's definitely lied. What he has said is false, and there might be some consequences to his actions. So when is the dot true? So what we'll be trying to do is go from the truth value of simple statements to the truth value of entire propositions. So if our entire proposition was P dot Q, and we knew that P was true and Q was true, then we'd know that our entire proposition was true. If any part of P and Q was false, then we would know that P and Q, the statement, was false. So when is the dot true? This is the way I'll be talking about these. When is the dot true? Only when both parts are true. In any other case, it's false. All right, so the next thing we'll want to talk about is disjunction. So disjunction is the wedge, here to symbolize words like or, unless, either, sometimes, things like that. So when is P or Q true? Let's say, again, you're at the same restaurant, but you're a little less greedy with dessert this time. You say you're okay with pie or cake. So the waiter tells you, okay, you're getting pie or cake for dessert. Under what circumstances is that true? Under what circumstances is that false? Well, the waiter tells you you're getting pie or cake. Let's start from the bottom here. Imagine it's false that you get pie and it's false that you get cake. Then the waiter saying you're getting pie or cake is clearly false. You didn't get any of them, and he said you'd get pie or cake. Very clearly not true. What if he doesn't? So what if it's false that he brings you pie, but it's true that he brings you cake? Well, in that case, he said you'd get pie or cake. It's very clear that it's true. You got cake in this example. What if it's true that you get pie, but it's false that you get cake? Then what do we think of the statement, you're getting pie or cake for dessert? We think it's true. Why? Because you got the pie. So true that pie or cake, that you would get them. Now here's where it gets a little bit weird. But let's go back to my example and then I'll talk more about this issue. Let's say you say, I'm fine with pie or cake. The waiter tells you you're getting pie or cake for dessert. And let's say it's true that you get pie and it's true that you get cake. If you're like me and you have a real sweet tooth, you're not going to immediately call the waiter out for being a liar. He brought you both. You're happy that you got pie or cake. So you don't call him out for being a liar. You just say that it's true. Now that's one way to think about this. Another way of getting your head around why logicians might have decided to go with this type of disjunction is the following. So there are two types of disjunction in our language. There are inclusive disjunctions and there are exclusive disjunctions. So an exclusive disjunction is one or the other but not both. You can think of examples like the light is either on or it's off, but it's not both. So it's one or the other, not both. An inclusive disjunction we also find in various places. So imagine a situation where, let's say there was a prerequisite to getting into this class. Let's say that before you get into Philosophy B7, you either had to pass Philosophy B6 with a C or higher, or you could take a standardized test and get 70% or above on that standardized test. Now, if those are the prerequisites for the course, it's clear that if you got a B in the class, if you got a B in Philosophy B6, you'd get into B7. Or if you got 70% or higher on that standardized test, so say you got a 90%, you'd clearly get into the class. But what if you got both? If you got both, if you passed Philosophy B6 with higher than a C, and you got higher than a 70% on the standardized test, so both P and Q were true. Would we say that you got into the class in that circumstance? Yes, we would say that that would be the case, even though we would phrase the prerequisite as an or. We'd say you can take B6A and pass, or you can take the standardized test and get a 70% or higher. Even though we'd phrase that as an or, we would also include people who did both things. So that would be an inclusive disjunction. Logicians could have chosen to have this as an inclusive disjunction or as an exclusive disjunction. They chose to have this as an inclusive disjunction. No worries, we can make an exclusive disjunction. We could do in parentheses P wedge Q, and so a dot and in parentheses, and then a tilde, open parenthesis, P dot Q, close parentheses. So we could have P or Q and not both P and Q, and that would be an exclusive disjunction. If all of this is leading you astray, just know this. As long as some part of our wedge is true, then the wedge is true. The only case when the wedge is false is when both parts of it are false. All right, so now let's look at conditional statements. So if P, then Q, P implies Q, Q given that P P is a sufficient condition for Q, Q is a necessary condition for P. All of these are ways of saying we translate the same way to our symbolic language, P horseshoe Q. So when is P horseshoe Q true and when is it false? Consider the following scenario. Imagine you live in a very rural area and you drive through an area to get to school and to get to work where there's quite a lot of wildlife. Specifically, there's a lot of deer, and you're very worried that you're going to hit a deer. So you think to yourself, well, I'm going to take out an insurance policy in case I hit a deer. So you go to an insurance salesman, insurance agent, and he tells you, you're in luck, we have the perfect policy for you. Here's a policy where if you hit a deer, then we'll give you a pile of money. Now, under what conditions would you know that the agent's statement was true, and under what conditions would you know it's false, and when would you not know one way or the other? That we should talk about. So the agent said, if you hit a deer, then we'll give you a pile of money. Imagine you sign on the dotted line, you get that policy, and then imagine you drive off the lot, and then you hit a deer. So it becomes true that you hit a deer. And then imagine you call up your insurance agent and lo and behold, he gives you a pile of money. So Q is also true. In this case, it's true, horseshoe true. So what do we say about the whole statement? We'd say that shows that some evidence we'll say that the conditional statement is true in that circumstance. So that's pretty easy. What about the next case? So imagine you sign on the dotted line, you get that insurance policy. Again, that policy is if you hit a deer, we'll give you a pile of money. Imagine you drive off the lot, you hit a deer. Imagine you call up the insurance agent and they fail to give you a pile of money. It's false that they give you a pile of money. Well, then what do you know about what the agent said? Here, you know for sure that what the agent said is false. You have a perfect, what's called a counterexample to what the agent said. He said, if you hit the deer, we'll give you a pile of money, but he didn't give you a pile of money. So you know that what the agent said is false. Again, that's pretty straightforward. Now here's where we get into some weird cases. So imagine again, you get this policy where if you hit a deer, then the agent will give you a pile of money. And imagine you never hit a deer, so it's false that you hit a deer. But imagine your insurance agent calls you up out of the blue and he's like, here's a pile of money for you. Is what he said false, that if you hit a deer, then we'll give you a pile of money? You're not sure. All that you know so far is you haven't hit any deer, but he still gave you money. Now, if you called him out and you said, wait, what you said is false. You said, if I hit a deer, you'd give me a pile of money. But you gave me a pile of money, I didn't even hit a deer. He could justly say to you, well, I never told you what would happen if you didn't hit a deer. I may give you money, I may not if you don't hit a deer. But all I said was, if you hit a deer, then I'll give you a pile of money. And you still don't really know whether that's true or false. You don't have a test, you don't have the case that you would need to demonstrate the truth or falsity of, if I hit a deer, then he'll give me a pile of money. He hasn't told you about a world where you don't hit deers. So in this case, we just assume what the agent was saying is true. That if we hit a deer, if I hit a deer, he would give me a pile of money. Because this won't show that this is false. Consider another case where you sign on the dotted line where it says if you hit a deer, then the agent will give you a pile of money. You never hit a deer, you call up your agent and you're like, I never hit a deer. And he's like, cool, I'm not giving you any money. What should we think of his conditional statement? Well, certainly we can't say that it's false because all he said was, if you hit a deer, I'll give you a pile of money. He didn't say what would happen if you don't hit a deer. So the fact that it's false that he gave you money doesn't show that this whole statement is false. So what should we think about that whole statement? Well, it very well may be true. in this case. So what general rule of thumb can we take away for conditional statements? The only case where we know a conditional statement is false is if the antecedent is true and the consequent is false. If that is the case, then we know a conditional statement is false. If anything else is the case, we don't know that it's false, so we just put that it's true. So the only time a conditional statement is false is when it's true, horseshoe, false. Or at least that's the only time we can tell it's false. So for every other instance, every other case, we put true. So there's some interesting things that fall out of that. If you have a false antecedent, then you have a true conditional statement. If you have a true consequent, then you have a true conditional statement. The only time when the horseshoe is false is when it's true, horseshoe, false. Then you would say the statement is false. All right, finally, what about the biconditional? So the biconditional is the triple bar. The triple bar represents, it was what we would translate, well, if and only if something is a sufficient necessary condition for something else, we would translate that as a triple bar. Or on our keyboard, just an equal sign. So what is the truth table for that? I've actually already filled it in. It's true, false, false, true. So in what circumstances, how do we see that that's true? Well, for the biconditional, so take a statement like, if a team wins the Lombardi Trophy if and only if that team wins the Super Bowl. It's a biconditional. What's that saying? It's saying, if a team wins the Lombardi Trophy, then they won the Super Bowl, and if they won the Super Bowl, then they won the Lombardi Trophy. So this triple bar, this in our keyboard language, equal sign, is actually shorthand for two statements conjoined together. If P then Q, and if Q then P. So what about the case when P and Q are both true? Well, then we would have true, horseshoe, true, and going up to the conditional up here for the horseshoe, when it's true, horseshoe, true, that means the statement is true. So we'd have this statement being true, and we'd have Q, horseshoe, P, where Q is true and P is true, so we'd have true, horseshoe, true. Again, looking at the conditional statement table, we'd see that that is true. So we'd have true conjoined with true, so true and true, a statement that's true and another statement that's true, so then the dot itself would be true. So that's how we get that this is true. What about the case where P is true and Q is false? Well, if P is true and Q is false over here, then we'd have true, horseshoe, false. And what would the truth value of that be? Well, in fact, that's the only case when the horseshoe is false. So we'd have this as false. And then over here we'd have false, horseshoe, true, which if you look up to the table of conditional statements, you'd see is true. So we'd have a false statement and a true statement. So what would the truth value of that be? The truth value of that would be false. Because for the conjunction to be true, both parts have to be true. Instead of going through this, each line, going through this equation and showing you how we work through it to get these results, we'll just go with these results and you can trust me for the next two lines. Now, what sort of shorthand can we have for the biconditional then? Well, something emerges on some inspection of this table. If the values on both sides of the triple bar are equivalent, so if it's true, triple bar true, then the statement is true. And if it's false, triple bar false, so if it's false on both sides, then the triple bar is true. So when is the triple bar false? When the values on either side are not equivalent. So when it's true, triple bar false, or false, triple bar true. then the triple bar is false. So the triple bar, I mean, it's nice that on our keyboard it's an equal sign because it functions sort of like an equal sign. If the things on the opposite sides are the same, the triple bar is true. If the things on the opposite sides are not the same, then it's false. And we end up with something that looks like this. All right, so that's how all of the that is the truth functionality of all of the operators. Besides that, we need one more tool in our toolbox in order to figure out the truth value of long propositions. And that is, we need an order of operations. Well, a couple things. We need to figure out the main operator of propositions, and we need an order of operations. So here's what we've covered so far over here on the left-hand side. These are just the truth tables of all of the operators that we've covered so far. So then, let's talk about this idea of the main operator of a proposition. So here's the definition. The main operator is the operator outside all parentheses, brackets, and braces. If there's more than one, then the main operator is not the tilde. All right, so let's practice applying this definition. So what is the main operator of number 1 here, this proposition? Well, to find it, we have to apply the definition. So it's the one outside all parentheses, brackets, and braces. There are two operators here. There's a wedge and a dot. Which is the main operator? Well, the dot is inside the parentheses, so it's not going to be that one because the main operator is outside all parentheses. The wedge is outside the parentheses, and it's the only one outside all parentheses. So the wedge, in fact, is going to be our main operator. So let's go down to number 2 here. So 2, we have the same proposition, but we just added a tilde in front of the A. So now what's the main operator of number 2? To figure it out, we go back to our definition. Well, we have 3 operators. Let's start there. We have a tilde and a wedge and a dot. And we're told that the main operator is outside all parentheses, brackets, and braces. There are 2 of those. There's a tilde and there's a wedge. So which of those 2 is the main operator? If there's more than one, the main operator is not the tilde. So again, the main operator here would be the wedge. What are we trying to do here? What we're trying to do is find the operator that has the largest scope. In this first proposition, the dot had a restricted scope. The dot brought together the B and the C. The wedge, however, has the scope. It brings together the A with the B and the C. So the scope of the OR is just like a big OR. It's like on the one hand A, on the other hand B and C. Similarly here, the dot, what's the scope of the dot? Or sorry, not the dot, the hyphen or the tilde, what's the scope of it? Just the A, that's all it's negating. So that won't be the main operator. This is still an on the one hand or the other sort of proposition. Now let's go down to this one as a nice point of contrast. So here we just added a tilde before the entire proposition. So what's the main operator? Well, we're told that the main operator is the operator outside all parentheses, brackets, and braces. Here's the parentheses, the dots in there. Here's the bracket and the, I can't get to it, but the tilde and the wedge are in there. What's outside of everything? Just the tilde. So what would be our main operator? The tilde. Now, there are 3 more practice problems here where you'd find the main operator. I suggest you pause the video and do 4, 5, and 6 and find the main operator of all those. I'll pause for just a second so you can do that, and when we come back, I'll tell you what the main operator is. So pause the video and do the work now. All right, so the main operator of number 4 we had the same proposition as number 3, except we added this part at the end. And now the operators that are outside everything are that tilde, this triple bar, and that tilde. And we're told that we have the main operators outside everything, and if they're multiple, it's not the tilde, so the triple bar was our main operator. Here we have this, and number 5, we have this whole equation put into braces, and then y dot added. The only operator in this case that's outside everything is the dot, so that's our main operator. And then we added a z wedge before the y, put that all in parentheses, and we still had over here our original proposition up there. So what's the only thing that's outside of everything? Just the dot is outside of everything. So that will be our main operator. Hopefully that was fairly straightforward. Now, the last thing that we need is an order of operations. So when we're calculating the truth value of longer propositions, we need an order of operations. So the general strategy is to build the truth values of the larger components from the truth values of the smaller ones. In general, the order to be followed in entering truth values is this. First, when you're given a long proposition, enter the truth values for the individual statement variables. So the capital letters will be given a key, and we enter the truth value that the key gives us right underneath the letter. Then the next thing we would do is if there are any tildes immediately preceding the individual letters, we would flip those truth values, because that's what the tilde does, it flips truth values. Then we would deal with operators that join letters together. In general, I go from inside parentheses out and build up to larger structures in the propositions, tildes immediately preceding parentheses, etc., etc. This order of operations will make a lot more sense as we start solving problems. So let's start doing that now. So let's say we're given the key. A, B, and C are true. Those statements are all true. And X, Y, and Z are all false. Let's do some practice problems. So let's say we were given this: if A or X, then Z. And we need to figure out the truth value of this entire proposition, given that A, B, and C are true and X, Y, and Z are false. So the first step we need to do is fill in the truth value for the individual letters representing simple propositions. So here we have A. We're given in our key that A is true, so we're going to put true under A, and we're going to make that lowercase for reasons which will become apparent. And X, we're given in our key that X is false, so we're going to put that under there. And Z, we're given in our key that Z is false. So we have entered the truth value of the simple propositions. Now it's time to, if there are any tildes immediately preceding individual letters, we would figure out we would flip these truth values. There are actually no tildes here, so we don't need that step. So the next thing that I would urge us to do is go inside the parentheses and assign truth value to the statements brought together by our two-place operators. So we have A wedge X. So here we have part of a wedge that's true. Remember, the wedge is or. So A or X. Is that proposition true or false? To figure that out, if you don't know it off the top of your head, we go to our chart over here with P wedge Q. So here our P is A and our our Q is X. So we are told that A is true, so our P is true and X is false, so our Q is false. So true, wedge, false. So we're looking for this line where the first part is true and the second part is false. In that case, our table tells us that the statement is true, and it makes sense. If I tell you you're getting pie or cake for dessert, you get pie, but you don't get cake. That statement is the statement that I made was still true. Now I'm going to put a capital letter for that to denote that I'm talking about an entire proposition here and not just these simple statements. So I'll put a true there. Now that tells me that this whole thing is true. So now what am I left with? I'm left with here everything in the parentheses is true, and this is the main operator, the horseshoe, and I'm left with true, horseshoe, false, or Z is false. So what's the truth value of that going to be? Well, for that I have to look at my chart for conditional statements, and I know that the only time horseshoe is false is when the antecedent is true and the consequent is false. And that is in fact what's going on here. I have true, horseshoe, false. So I know that that whole proposition is false. And that is my answer. Once you get to the main operator, your work is done. So you build up the truth values of the simple propositions to the more complex propositions, and once you get to the main operator, the operator that has as its scope the entire proposition, then your work is done. You can say whether the proposition is true or false. All right, let's try another example here. So here we have tilde z dot x horseshoe y. How would we say this? It is not the case that z, or let's do z is not the case, and if x, then y. There we go. So how will we do this? Well, we follow our order of operations. First, we do the individual letters representing simple propositions. So we fill these in from our key. We're told in our key that x, y, and z are false. In fact, that's what we have here. We have x, y, and z. So all the parts of this statement are false. But that does not tell us that the entire proposition is false. So we have false there, and on the other side we have false and horseshoe false. Alright, so now we're going to work our way up to the main operator. So what's the main operator? It's the one outside everything, but that's a tilde and a dot. And if they're two, it's not the tilde. So it's the dot. We're going to be working our way up to the dot. Once we get a truth value under the dot, then we have solved the truth value of the proposition. So what's our next step? Tildes immediately preceding individual letters. So here we have z as false, and the tilde will flip that. It'll flip it to true. Let's line these up a little better. There we go. So now we know that tilde z is true. And now we have to keep working. We'll work what's inside the parentheses now, is what I recommend that you do. So we have false, horseshoe, false. Now, is false, horseshoe, false? Do we consider that a true statement or a false statement? To figure out, we'd have to go down to our chart for conditional statements. And x is our P and y is our Q. They're both false. So we need the case when P and Q are both false. That's right down here. And the truth value of that statement, that proposition, is true. So when it's false, horseshoe, false, it's true. Many ways to remember that. One way is the only way a horseshoe is false is when it's true, false, and here we have false, false, so it's got to be true because the only time when it's false is true, false. Another way is if you have a false antecedent, like we do here, you can know that the entire conditional statement is true. All right, so what are we left with? We're left with true and true. What's the truth value of that? Well, we look at our chart. It's the only time when a conjunction is true is when both parts of it are true. So we write true under this. And that is our answer because we've got to the main operator. Now, that's the basics of what we're doing here. Now, given just the tools that I've given you so far, we can already solve the proposition that I talked about at the beginning of this lecture. So now we have the truth functionality of our operators. We understand where to find the main operator. We understand the order of operations that we need to follow to figure out the truth value of complex propositions. At the bottom here, I have some practice problems, including the problem that I initially set for you. So let's do those for practice right now. Let's give us the same key. A, B, and C are true. X, Y, and Z are false. I'll allow you to pause the video and solve these propositions yourself. And when you're ready to unpause it, when you've solved all the problems, come back and I'll go through them myself. So pause the video and do those problems. Remembering that A, B, and C are true, X, Y, and Z are false. Pause the video and do those problems now. Okay. Hopefully those problems went well for you, so I'm going to go through them myself. I'm going to go through them fairly quickly. Let's see here, true, X is false, A is true, Z is false. This tilde is the thing we would do first. The main operator here is the wedge. That's the last thing we'll be coming to. This tilde would flip that true, would flip that false to, why can't I do true? Flip that false to true. This tilde would flip that false to true. And then we continue to solve. So over here now we have true, horseshoe, true, and that is true. So now I know that for all of this, what's under the main operator of just this statement is the horseshoe, and I had that as true. True, one side. Now the main operator of this entire thing is a wedge, and now I know that one side of it's true. As long as one side of the wedge is true, then the wedge is true, because look at over here at disjunction, the only time when it's false is when both are false. As long as one part's true, then it's true. So I know my wedge here is true. And that's my answer. All right, for the next one, I have Z as false, I have X as false, I have Y as false. False and false is false. The tilde would flip that to true. I'm not going to line this stuff up because it's going to take too long. So then I have false, triple bar, true. So that is false. The triple bar is only true when both sides are equivalent in truth value. In this case, they're not. It's false on one side, true on the other. So that is false, and that's my answer there. Here, the main operator is the tilde, so that's what I'm going to be working up to. So first, I'll start by entering the truth values of the statement variables, true and true, and then I need to start solving. So first I'll do truth value. I'll do the tildes that affect individual letters first. So that tilde will make that a tilde a false, and this will flip. The B was true, but tilde B is false. So then I keep solving. I'll do inside, well, I won't even do that. So here I have a dot as the main operator for what's inside the parentheses, inside the brackets here. False on one side of the dot. In order for the dot to be true, both sides have to be true. In any other case, the dot is false. And here I know that one side is false, so I know now that this dot is false. So I know this proposition, sorry, I can't really highlight it without getting everything. This proposition is false inside here. And now the tilde will flip it to true. So the final answer is true for that one. Here we have a very long complex proposition, but there's a very short way to do it. X is false. The main operator here is a dot. One side of the dot is false. I know if the first part of the dot is false, it's false. In fact, if any part of the dot is false, it's false. So if either side of the dot is false, then it's false. So I know just by knowing X is false that this whole thing is false. That's a strategy to save yourself some work. The strategy, I'll talk about it just a little bit. I look at the main operator of these propositions and I ask myself, what do I know about it? And is there any way I can know that it's true or know that it's false just from knowing one part of it? And with a dot, I know the only time it's true is when both sides are true. So if I know that one side is false, then I know the whole proposition is false. But if you did the whole thing, that's all good. You'll have time on the test to do all the work. All right, so similarly, here I have a long proposition where the consequent is, the main operator is a horseshoe, the consequent is true. What do I know about horseshoes when the consequent is true? Conditional statements, the consequent is true here, and the whole proposition is true, and it's true here, and the whole proposition is true. So just in virtue of knowing that A is true, I now know the whole proposition is true. If you did it the long way but got the same answer, all good. If you did it the long way and got the wrong answer, then something got messed up along the way. Because once the consequent of a conditional statement is true, you know it's true regardless of what the results of the antecedent are. And finally, for this complicated, seemingly complex proposition, what is it essentially? What's the main operator? It's this wedge. There are two operators outside of everything, the tilde and the wedge. And the wedge, if there are two, it's not the tilde. So the main operator is the wedge. What do we know about wedges? As long as either side of the wedge is true, then the wedge itself is true. So here we have Z is false, but the tilde flips that to true. So tilde Z is true. Tilde Z is one part of the wedge. So this wedge is true regardless of what happens over there. Again, if you did it the long way and you got the same answer, great. If you did it the long way and got a different answer, then something went wrong. All right, great. So now there's one more little wrinkle that we have to cover, and that little wrinkle is, what if we don't know the truth value of some of these statement variables? So imagine in our key here, we have A, B, and C are true, X, Y, and Z are false, and P and Q have unknown truth value. Can we solve for the truth value of propositions even when the truth value of some of the statements is unknown? Sometimes we can, sometimes we can't. So we have to figure out if the following propositions are true, false, or if the truth value is unknown given the information we have. We'll follow the same order of operations. The operators act in the same way, so everything's the same. We'll just need to add a new symbol to our repertoire here. And we'll just use a question mark for short. So what if I have a wedge? If I'm trying to figure out if A wedge Q is true or false, and I know that A is true, but Q, I don't know. It has an unknown truth value. So I'll put true under the A, I'll put a question mark under the Q. Can I figure out if A or Q is true if I just know that A is true? If you can't think of it just in those terms, you can look at the table and see, well, what happens when the first part of the wedge is true? The wedge itself is true. So we can figure this out just in virtue of the information that we have. We know that this statement is true. All right, how about the next proposition that we have? P and not Z. So again, we don't know the truth value of P. We know that Z is false. So P, we have a question mark. Questions about P. Z is false. Can we figure out P and not Z? So we'll follow our same order of operations. So first, we do the statement value, the truth value under the letters. We already did that. Then we do tildes that affect individual letters. So the tilde will flip this to true. So then we have question mark and true. What's the truth value of that going to be? Well, we look at the table for the dot. In order for the dot to be true, both sides have to be true. Here we have one side is true, but we don't know about the other side. If P is true, then this statement is true. If P is false, then this statement is false. So everything depends on the truth value of P here, and we just don't have it. We could be dealing with either this circumstance, or we could be dealing with this circumstance. And in one of those circumstances it's true, and in one it's false. So we don't know the truth value of this, so we would say unknown. We can't figure out with the information we've been given. All right, so let's have you do the same thing I just did for the rest of these practice problems. Given that A, B, and C are true and X, Y, and Z are false, and you don't know the truth value of P and Q, let's do these practice problems to see if we can solve for the truth value. And the truth value you come out with could be true, or it could be false, or it could be unknown with the given information. So take some time to do that. Pause the video now and complete the rest of those problems. Complete the rest of those problems. All right, so hopefully those went pretty well. Let me go through them. We know here X is false, and that's the first part of a horseshoe. It doesn't matter if we know the rest, because if the antecedent is false, then the conditional statement is true. So that one we know is true because the antecedent was false. How about Z or tilde P? Z is false. P, we don't know the truth value of. So we won't know what the tilde is going to do to it, so we just don't know the truth value of tilde P. Lots of questions over here. We know that Z is false. From that, can we know the truth value of the wedge? Well, for a disjunction, if any part of it's true, then it's true. The only time when it's false is when both are false. This could either be where both sides are false, or it could be where it's false and this side could be true. So we don't know the truth value because we could be dealing with false true, or we could be dealing with false false, and the truth value of the entire proposition varies depending on which circumstance we're looking at. So for this, we do not know the truth value here. How about tilde, if Q, then Z, and horseshoe A. So we are given question mark, and for Z, we know that's false. For A, that's true. We can save a lot of work here if we forget about all this stuff over here, because we know if the consequent of a conditional statement is true, then we're either looking at this case or we're looking at this case. In either case, they're both true. So this horseshoe is true, and that's our answer. So how about this one? In this one, B we're given as true. A we're given as true. We don't know the truth value of P. So, do we have enough information to figure out the truth value of this statement? So, we'll follow our order of operations. There are no tildes that affect individual letters, so we'll start inside the parentheses. Well, first, I'm dealing with a dot, so it has to be true on both sides in order to be true. One side is true, so it will depend on what the other side is as to our truth value. So, here we have true, horseshoe, question mark. What can we say about the truth value of this conditional statement? Well, we could have, that could be true or false, because we could have true, horseshoe, true, or we could have true, horseshoe, false. We don't know what the truth value of this P is, so we actually don't know what the truth value of this entire conditional statement is. Whatever its truth value, the tilde would flip it, but we don't know what it was, so we don't know what it's flipped to. So now we have true and question mark. Is that going to be true or false? Well, we don't know unless we get the truth value of that second proposition, because it could be true or false. So this also is unknown. We don't know the answer to that. How about Q? Triple bar tilde Q. If we go with the method that I've been recommending so far, putting question marks underneath the statement variables that we don't know, then we would see that we don't know the value of Q, so we don't know the value of tilde Q. And then now we have question mark, triple bar question mark, so we wouldn't be able to figure out from that way of looking at the problem whether it was true or false, because it could be true, it could be any of these combinations, and some of those are true and some of those are false. So given this way of looking at it, we wouldn't know. But our method of looking at this actually fails us here, because there are two instances of Q. So Q is either true or it's false. We just don't know whether it's true or false. So what about the case where Q is true? Well, then this true would be flipped to false by that tilde. So tilde Q would be false. We'd have true, triple bar, false. We see that true, triple bar, false is false. So if Q is true, then this proposition is false. What about when Q is false? If Q is false, oh, come on, man. If Q is false, then this tilde would flip it to true. So if Q is false, then tilde Q is true. And then we'd have false triple bar true, and false triple bar true is also false. So going through it that way, we see whether P is true or whether it's false, this statement Q triple bar tilde Q is necessarily false. So our method of doing it failed us. In the homework, you'll actually see an example like that. But hopefully after I did that, it makes sense. So when you see the same variable on both sides, it might get a little bit more complicated, but usually that won't be the case. All right, so what have we covered today? We've covered the truth functionality of all 5 operators that we have in our language. We've covered the order of operations that we do to solve these problems. That order of operations includes figuring out what the main operator is. And with those 3 pieces, the truth functionality of the operators, the order of operations, and figuring out how to find the main operator, we can figure out the truth value of complex statements if we're given the assignment of truth values for the simple statements that they contain. This was the proposition that we had at the beginning, and we were able to solve that. Hopefully this lesson helped to figuring out how to solve these problems. These are the kinds of problems you're going to see on the test, and we're going to build on this foundation. In the text, you'll see they'll solve some of these problems by going down multiple lines and doing truth trees. I don't teach that method because we're eventually going to be needing to solve multiple kinds of these problems to solve one problem, sometimes up to 32 or 64 iterations of these problems to solve more complex problems. So we'll need to get to the point where we can do these on a single line. So I just teach the single lines up front instead of doing the truth trees that go down a page. If you're more comfortable with the truth trees for now, that's fine. By Wednesday's class, you'll need to be, or by whatever the next class is, you'll need to get beyond that. So I will see you next time.